So now we're looking at the second module now, basic algebra. So it is on determinants. So determinants are defined. Determinants are defined for a square matrix. It means that the number of rows, the number of columns for that matrix should be the same. So determinants will be if entries in your matrix are real, well, you end up with a real number. If they are complex valued, you end up with a complex number. So you just get a scalar or a field, and that is a result of finding a determinant for a matrix. So determinants enable us to be able to analyze properties of a matrix or systems of equations and other things. That number is important. So let us look at start with definition. So we have a square matrix A, which with the element AI. So if it is order two or more, if it is an element of order 1, which just becomes a real number, the determinant just becomes the number itself. So we're going to use two things in our definition, because the definition that we use is the Laplace definition. So we are going to first of all define what is called a minor of a matrix. The minor of a matrix is for each element in the matrix, each element I, you delete each element Aij, you delete the ith row and the jth column. So you have a matrix which is determinant, the determinant of that matrix which is an order less than 1. Then a cofactor is what we call a signed minor. You have to assign a sign to your minor there. And then this is obtained by -1. You raise it to the sum of the row position and the column position of your minor. So once you have your cofactors and your minors, you can now define a determinant. So the Laplace determinant, which is what we call the Laplace expansion of a determinant, you can use a row I, any row or any column, any row from the first one to the last one, from row 1 to row n, the first one. So it is equals to, you write it as the sum of the coefficient, the sum of the entry itself multiplied by its cofactor. So if you are using a row I, what is going to change is the column. The columns are changing from 1, 2 up, right up to n. If you are using a column J, starting from 1 to A, the determinant is just the same as this. But what is going to change is the i's. The J is fixed. So what is important is that this, which we are putting up in red, is what is called the invariance property. It means the value of the determinant is unique, and it remains the same regardless of which column or row which is selected. So you can use any row and any column to find your determinant. So that is a very powerful property. So we'll see later on when we evaluate determinants that will take advantage of that. So you can use any row or any column. So let us look at an example here. You want to evaluate the determinant of that 4 by 4 matrix, 4 rows, 4 columns. So from what we've just mentioned, we said you can use any row or any column. So the strategy is that if you use a row which have non-zero entries, you evaluate 4 rows. If I use this one for example, I will evaluate 4 3 by 3 matrices, which in themselves are not a walk in the park to evaluate. So you need to do the 4 3 by 3 matrices, which will in turn, if you expand using this Laplace method, in turn you have another 3 2 by 2 matrices. So it is like 4 times 2 times 3. You evaluate 4 2 by 2 matrices. But you can reduce the number of the operations if you see where there is a 0. So there are 2 zeros in the third row, and there are 2 zeros in the fourth row. So the strategy is just to use the number of rows that you have, which has more zeros. So, and another thing is that even if you have rows, you can introduce zeros by performing elementary row operations to introduce another 0 so that you only have 1. You just only have 1. So you can perform row operations, eliminate zeros in the other 3 entries in a row or a column. And then if you do that, you will just be left with just evaluating a single 3 by 3 matrix, which you can approach the same strategy and reduce it to evaluating just one 2 by 2 matrix. So that is the strategy. You expand along the row or a column which systematically reduces the order of the determinant. So let's see how we do this for this matrix. The first stage is to reduce the order from 4 by 4 to 3 by 3. So we have identified that column 4 contains 2 zeros. There are 2 zeros there. So we can create a third zero. We can create a third zero if we do this row operation. So after performing this row operation, where we make row 1 equal to row 1 minus row 2, there will be 3 zeros there in column 4. So now we can expand using column 4. So column 4, if we expand this determinant, all the others are going to be 0, except when you eliminate row 2, column 3. Row 2, column 3. So the 2 comes down, it's multiplying there. Then this is your sign for your minor, that's your minor matrix. The minor matrix that will remain is minus 3, 2, 5, 3 minus 2, 5, 0, 2, 1, 0, 2 minus 1, 3, 1 minus 2, which is just this matrix. We want to find its determinant. So we are going to have, this is going to be a plus here. So because of you are raising to the power 6. So it's going to be 2 times that determinant of B. So this now B, let us do the same thing. We are saying there is a 3 here, but we can also reduce it by subtracting this 2. If we perform that row operation, it will not change the determinant. So we're going to do that with the 2, with the 3 matrix. That is our second stage. So we're going to reduce the order from 3 by 3 to 2 by 3. So in the matrix that we have B, column 1 is a 0, this one. And we can eliminate B3 by using row 3 minus row 1. So you end up with the determinant of B being this determinant here. The determinant, now we have zeros there. So you can now expand using column 1. So you use column 1, then it's minus 1, 1 plus 1. What is remaining is this 2 by 2 matrix here. 2 minus 1, 3, 2. So you just need to find this determinant. So you see how much work we have reduced by just using row operations. You now have that's 3 times 2. So this is the determinant. Evaluate this determinant. It's just a 2 by 2 determinant, which we know how to evaluate. It's just a 2 by 2 determinant which you know how to evaluate. So the 2 by 2 determinant, alright, the 2 by 2 determinant so let's go back to where we were. Let's go back to where we were. What is happening here? Just get me the right. Let's just get it to that point. Okay. So if you go up, we're saying we're at this point where we're going to evaluate this 3 by 3 determinant. So if you are going to evaluate this, it is just the determinant multiplying is AD minus BC, the usual 2 by 2 matrix determinant, which we know. So the determinant is minus 3. So we can now, we know the determinant of B. The determinant of B is 3 times minus 11, so it's minus 33. But to get the determinant of A, this was 2 times the determinant of B. So in our case, we are going to get our determinant as being equals to minus 66. So the determinant of that matrix is minus 66. Determinant of that matrix is minus 66. So that's how we find the determinant of matrices using the Laplace expansion. The trick is to use rows which have zeros. And if there are no zeros, we introduce them by using row operations. These row operations, the third row operation, where you add a scalar multiple of the other one, does not change the determinant. So the determinant will remain the same. The determinant will remain the same. So introduce zeros using row operations to fundamentally reduces your work. So let's stop here for now.